In this lesson, I'm going to show you how to draw orbital notations and then electron configurations. Between the two, the most important for standardized tests is electron configurations. I really believe that's just because they're easier to use the computer to word process. And even though orbital notations you won't see as much, in my personal opinion, they are way more helpful for you using this type of quantum number electron structure to solve problems for bonding later on. To get started, let's talk about some principles. There's three of them that we used to complete the structure of the electron cloud. The first is the Offball Principle. Offball is not a person. It's a German word that means something about energy, like the order of energy or something like that. But it very simply states electrons are placed in the lowest energetically available subshell. In other words, when we build the electron cloud and we start putting electrons there, we start with the lowest energy, which is closest to the nucleus, which is the 1s orbital. And then once the 1 is full, we go to the second energy level, and then when it's full, we go to the third, and the fourth, and so on. So the energy increases as you go out ring by ring by ring. This diagram on the screen on the left-hand side is called an off-ball diagram. What it also does, in addition to looking straight across at the energy levels themselves, it breaks each energy level up into its subshells and then also ranks them in order of energy. The diagram on the right also does the same thing. But to know the correct order to fill orbitals, we follow the arrows on an off-ball diagram. So we would go 1s, and then 2s, and then 2p3s, and then 3p4s, and then 3d4p. It doesn't get goofy until we get to the transition metals where the 3d kind of jumps out of place and goes beyond the 4s. In other words, we put the 4s before the 3d. The diagram on the right might do a better job of explaining what and why. Each one of these columns represents an energy shell, an energy level. It's a little off-centered as it's written. But as you go up the y-axis, each energy subshell has a higher value. So we can see that it goes pretty much in order. The 1s is pretty low, and then the 2s, and then the 2p, and then the 3s, and the 3p. But now what I want to show you is that the 3d actually has a higher energy value than the 4s. In other words, an electron in the 4s has a lower energy than an electron in the 3d does. So we put electrons into 4s first. Keep that off-ball diagram handy, especially as you're learning how to do this. You'll want to use that as a reference. The second rule we want to talk about is called Hunds Rule. Now, Hun was a person, and his rule says when several orbitals of equal energy are available, electrons enter singly and with parallel spins. So what we're talking about here with orbitals of equal energy, situations like that arise in the 2p subshell, because in the 2p subshell there are three orbitals, the 2px, the 2py, and the 2pz, and each of those three orbitals have the same energy value. So it is better to put one electron into each of those three orbitals first before you try to put a second one in. When you put the second one in, which is incorrect in the bottom picture, the second electron is going to have a higher energy than it could have because there is some repulsions that it has to overcome with its neighbor. Kind of like your siblings. If you have a 3-bedroom house and there's three of you, then each of you would rather have your own bedroom before any two of you have to share a room. and electrons are the same way. The third and final principle that we use to do this is called the Pauli Exclusion principle. And he says that no two electrons can have the same set of 4 quantum numbers. And it has to do with the spin quantum number. There are only 2 values of spin, positive 1/2 and negative 1/2. And spin has to do with a property, a quantum property of electrons. For them to be together, they have to overcome their negative repulsion. So they come up, they do this thing that we call spin. It is a property of oppositeness that they kind of just made up on their own to allow them to stay together. Not easily, but still they stay together. The bottom line is that when you do orbital notations, your arrows on an orbital, on a line or in a box have to go opposite directions. They cannot be pointing in the same direction. So let's do some orbital notations. Orbital notation uses arrows to represent electrons. We're going to represent all 4 quantum numbers in orbital notation, and that's why it is more useful and more powerful than electron configuration. It just so happens that the pictures I have on the screen are not fully showing the 4 quantum numbers. If I went and changed this to 2px, 2py, and 2pz, now that shows all 4 quantum numbers because you have n with the 1, you have L with the S. So level, subshell, and then the px's are m sub L, the orbital, and then individual arrows are m sub S, the spin quantum number. Practice, here we go. You'll want to have your periodic table out, so if you don't have it, hit pause and get it out of your notebook. We're going to start with hydrogen. Hydrogen has only 1 electron, being element number 1. So we begin at the bottom, the 1s orbital. And I do lines instead of boxes, that's just my preference. And we put 1 arrow. It doesn't matter if it's up or down. I, over the years, have an affinity for drawing up first. That's just my preference. So there's complete orbital notation for hydrogen. Moving on to helium. Helium has an additional electron, so 1 more. So now we have hydrogen, and we'll add 1 additional electron, and that completes the orbital and the energy level. The next element, element number 3, is lithium. Lithium would be 1 additional electron to what helium is. So the next available orbital is the 2s orbital, and we'd put that 3rd electron there. Okay, I'm going to skip an element now. I'm going to go to boron, which is element number 5. So we'll go 1s, up, down. Next is 2s, up, down. That's 4 electrons. Now the next thing I draw will be 2px, 2py, and 2pz. As we go into the 2p subshell, each of the 3 orbitals appears at the same time. They are equal energy. You can't just draw, or you shouldn't just draw 1. And then we will pick any of the 3 to put any direction arrow in. And I always go X first just because it's alphabetical order and makes me feel better. I could put it in the Y or the Z and it would be just as correct. So there's boron. Next, let's do nitrogen. Nitrogen has 7 electrons, so we will start out with 1s, up, down, 2s, up, down. There's 4 electrons. Then the 2p subshell appears, 2px, 2py, 2pz. And now we're going to apply for the first time Hunds Rule. I have 3 more electrons to put in, so I'll go up. And before I put down, I need to go to the other orbital, put up, and then to the 3rd one and put up. I do not want to pair any electrons in those orbitals until at least 1 is in each. All right, then oxygen. Oxygen is going to have just one more electron than nitrogen, so we'll have the 1s up, down, 2s up, down, 2px, 2py, 2pz, and then up, 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 down, down, and that's too many. That's what you call getting carried away. So fixing that, it was just up, 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 down, and that's 8 electrons, not 9. Sorry about that. And then we go to magnesium. Magnesium has 12 electrons. Won't you hit pause and try this one on your own? Use the off-ball diagram to predict what the next steps would be. Okay, let's check your work. 1s, up, down, 2s, up, down, 2px, 2py, 2pz. After the 2p's, we have to go to the next energy level where we find the 3s orbital. So for the p's, that's up, 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 down, down, down. That's 10 electrons. I need 2 more, so into the s orbital, up, down. And there's magnesium. Okay, and the next one, we're going to expand even further, this time going into the transition metals. So we've got some d orbitals appearing, and you'll love it. All right, so getting started with manganese. 1s, up, down. 2s, up, down. 2px, 2py, 2pz, up, 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 down, down, down. That's 10. Only 15 more to go to get to 25. So then we have 3s, up, down, that's magnesium. And then 3px, 3py, 3pz, up, up. Oh boy. Tell you, you can just get carried away doing this stuff. Alright, let's get back to doing it the right way here. So that is a 3py. So up, 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 down, down, and down. That takes me to argon. Now, on the third energy level, I do have d orbitals, but the off-ball principle tells me that 4s comes first. Those 2 electrons take me to 20, which is calcium. After that, now I have the 3ds. And the d orbitals are 3d xy, 3d xz, 3d yz, 3d x squared minus y squared, and finally 3d z squared. I have 5 electrons to assign to this, and the Hunds rule does apply. So that's going to be up, 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 and up. And there's my last 5 electrons. There's the complete orbital notation for manganese. All right, once you hit pause, why don't you try nickel? Nickel is just a few down from manganese, and I'll have the answer when you get back. Okay, I have most of nickel drawn in. Nickel has 28 electrons, so I've got the first 20 drawn in up through calcium. So I wanted to add the last 8 together. So here we go. Up, 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 and up, and that's what we had for manganese. And 3 more, down, down, and down. So we can see that nickel has 2 more places to fill in order to have a complete shell. That's going to affect its reactivity. It's going to do things in order to get these Ds at a lower energy. But that's another discussion for another lesson. We'll be back tomorrow night probably for the electron configurations.